Okay, let's look at covariance of x and y. So covariance is just defined as the mu 1, 1. So again, the mu's in this textbook are the center moments. So this is the expected value of x minus mx times y minus my. And it turns out that then you can multiply that out in there, right? This is the expected value of x times y minus my times x minus mx times y, and then plus mx my. And so then this is the expected value of xy minus my times the expected value of x minus mx times the expected value of y plus mx my. And so this is the expected value of xy minus my mx minus mx my, same thing, minus mx, plus mx my. And so we get expected value xy minus mx my. So again, here's our definition up here, but I'd probably calculate it this way. And so that's covariance. And now our correlation coefficient. Of x and y is called rho, and that is just our covariance divided by the two standard deviations multiplied together. So this is our expected value of xy over standard deviation of x, standard deviation of y. Okay, so that's correlation coefficient. And we're told right away that this number is, the absolute value. So let me write that way. Absolute value of rho is less than or equal to 1. They do a little proof of that. I'm not going to bother with the proof in here. And but taking this a little further, if x and y are independent, then we have that the expected value of x and y, x times y, is equal to 0, and so the correlation coefficient is equal to 0. And so they do a proof using the continuous, but it really doesn't matter. And so if we look at e of xy, I'll do it here, e of xy, remember that that's just the integral from minus infinity to infinity, minus infinity to infinity, of x times y times our joint probability distribution, dx dy. However, if x and y are independent, then this becomes the integral from minus infinity to infinity, minus infinity to infinity of x, y, fx of x, fy of y. The joint distribution is just the product of the two individual distributions if they're independent. And so, you get, if I separate things here, we have minus infinity to infinity of x f sub x of x dx, and minus infinity to infinity of y f sub y of y dy. But of course those are just the means, so that's m sub x times m sub y. Okay, so we have e of xy is that, but then remember that mu11 can be written, so mu11, which we're saying is 0, mu11, it can be calculated simply as e of xy minus mx my, and so this is mx my minus mx my, and we get 0. So indeed, if x and y are independent, then our covariance is 0, and the correlation coefficient is also 0. Okay, so a little more. If you think of these as vectors, okay, so as vectors, this is something that kind of comes up with data, or say a uniform distribution. If you think of as vectors, so this is kind of going to the discrete case, but as we do that central moment, remember that what we're doing, we're taking an xi minus m sub x, and we're taking an a yi minus m sub y, and so our expected value of x minus m x, whoops, there we go, y minus m y, right, that becomes, in the discrete case, now let's assume that we have a uniform distribution of some kind, so that our f of x and our f of y are, well, actually I should write that as f of xy, shouldn't I? Otherwise we're saying independent and everything's 0 anyway. So f of xy. So suppose, that's some sort of constant. Then in essence what this boils down to is that I am taking the sum over I in this case, if well, we'll assume that the two sets of data or the two distributions have the same number in them, and so we're taking the sum of the xi minus mx times yi minus my. Now, we also have the f of x in there, but if that's a constant, you can think of this as the dot product of an x vector with a y vector. Okay, now they're centered at the mean. We've subtracted the means off each one, but this you can kind of think of as x dot y. And then if you think of sigma x, right, that is the sum of the xi squared. Oops, xi, sorry, I forgot my minus mx squared, like that. And then we take the square root. Well, that looks a lot like the magnitude of a vector x. Similarly, sigma y looks a lot like the magnitude of a vector y. And so when you look at that correlation coefficient, you're sort of looking at x dot y over the magnitude of x, magnitude of y. And from linear algebra or calculus 3, what we know then is that looks a lot like the cosine of theta, where theta is the angle between the vectors x and y. Okay, so this correlation coefficient, it's in a way, from a linear algebra point of view, kind of looking at an angle. And so if the correlation coefficient is 0, then that would kind of imply that somehow the angle between these data, these data was 0, and if it's 1 or -1, the angle's more like pi over 2 or negative pi over 2. So that's just kind of an interesting geometric interpretation of the correlation coefficient. And then finally, I think, then on the correlation coefficient, how about the name? Correlation coefficient. Where the heck does that come from? Well, if one, say, wants to approximate and they sort of do it, what I would say looks a little backwards. So I'm going to say, let's approximate a random variable y with x by ax plus b. So y equals ax plus b. If we do that, so by that, by minimizing the expected value of y minus ax plus b squared. Okay, now you can solve this. This just becomes a minimization problem, and we call it a least squares. And so if we do that either by linear algebra or calculus, it produces that the best answer is A equal the variance of y times the correlation coefficient over the variance of x, and that B is the mean of y minus A times the mean of x. But you see that A is a coefficient, and there's rho showing up. And we already had names for these standard deviations. And so I've got the standard deviation of y, standard deviation of x, times rho to make a coefficient of x. And so that name, correlation coefficient, sounds pretty good. And the actual error, okay, that we would get from this is the variance of y times 1 minus rho squared. And so what we see is that if rho equals plus or minus 1, that implies the error is 0. And so what this is looking at is how well this the correlation coefficient helps us tell, since this is the error, right? The correlation coefficient helps us understand how well y can be approximated by ax plus b. In other words, is there a linear relationship between the x variable and the y variable? And that's a big use of the correlation coefficient. And so there we go. So that was covariance and correlation. I guess we're done with that.